So now we will use spectral sequence to get the long exact sequence associated with the homology of a pair. So recall that pair is this A comma B, where B lies within A. And for such a pair, you can have a filtration like this. X minus 1 is a subset of x0, which is a subset of x1. And this x minus 1 you set up as the null set. x0 you set up as B, and x1 you set as A. So you get a filtration for this pair AB. Now we start with page 0. So page 0 you set it as the pqth entry is cp plus q xp minus 1. But we only have two things. We just have x0 and we have x1. This is just the null set. So this is how our page 0 will look like. So we will just have two columns. The column corresponding to x0 x minus 1, so this pair, and the column corresponding to this pair x0 x1. So where x minus 1 is just the null set. So we are writing it like this: cp plus q xp minus 1. So here both p and q are 0. So notice this is pth term here. This is p right here. So p is 0 and therefore q is also 0. So again here p is 0 and q is 1. Here p is 0, q is 2. Obviously these are the coordinates. This is the 0 0 coordinate. This is 0 1. So p is 0, q is 1. This is 0 2. So p is 0, q is 2. This is 0 3, and so on. So this was our 0 column, and the only other non-zero column is the column 1. So here our first entry, so this is p is 1. So q is 0 because 1 plus 0 would be 1. So you have 1 0. Here again p is just constant 1, so 1, and this is 1. So 1 plus 1 is 2. Again p is just 1 and q is now 2. 1 plus 2 is 3. So we are doing p plus q. Again you have 1 here and q is 3. So 1 plus 3 is 4. So we should also have here c0 somewhere. I'm just going to skip it, but essentially you should also have this term here. Now what is c0? This will obviously lie in 1 minus 1. So everywhere else you have zeros. So if you look at further columns here, it will just have zeros here. And you look at the columns here on the left, it will just have zeros. So this is our page 0. Now we start taking the homology here and land up in page 1. So now this x minus 1 is just the null set. So this entire chain complex is just for x0. And you already know this x0 is b. So x0 is b. You start taking the homology, you get h3b, h2b, h1b, h0b. You start taking homology here. Notice that x1 is a, x0 is b. So the pair is a comma b. So you have h4ab corresponding to c4, corresponding to c3 you have h3, corresponding to c2 you have h2, corresponding to c1 you have h1, and corresponding to c0 you have h0ab here. So as I said before, we are not going to worry about this term here. So this is our page 1. Again, we are working in homology. So for page 0, you know, you have to move r left. So for page r, our convention is r left, r minus 1 up. So if you put 0 here, you get 0 left minus 1 up. So that is page 0. So minus 1 up means 1 down. Page 1, you have 1 left, 0 up. So that's why we have the arrows like this. And you call these arrows delta 1, delta 2, delta 3, and delta 4. So now you start computing homology of this. So you obviously have zeros everywhere else because the modules here are zeros. So your homology is submodules. So you have zeros coming in and zeros going out. So if you have something like this, then obviously its homology is just kernel of this map is the homology here, and co-kernel of this map is homology here. So next page, page 2, looks like this. So you have co-kernel of delta 4, kernel of delta 4 corresponding to this map. Co-kernel of delta 3, kernel of delta 3. Co-kernel of delta 2, kernel of delta 2. So again, homology here is co-kernel of delta 1, homology here is kernel of delta 1. homology here is kernel of delta 3, homology here is co-kernel of delta 3. So this is page 2, this is stabilizers. You can obviously see that arrow going out from here will land in 0, and arrow coming in here will come from here, because we are on page 2. So you will move 2 left and 1 up. So this arrow has to come from here because 2 beyond. So this is stabilized. Similarly for this is stabilized. Similarly this kernel is stabilized because obviously arrow coming in is coming from 0, but arrow going out you have to go 2 left. 1 is here and 2 is here. There's already zeros here. So this arrow going out will also land in 0. So everything is stabilized here. So from page 2 to page infinity we have this. So this is exactly how page infinity will also look like. So you know that page infinity gives us the homology, and the homology is essentially given by the anti-diagonal elements. So if you want to compute h1, you have to take these 2 elements, because this element corresponds to 1 0, this element corresponds to 0 1. Just like here we have written the coordinates right here, and the homology groups sit precisely where these modules are. So you have h1 here, everywhere else is 0, and you have h2 right here, direct sum of these two. h3 is right here. So if you want to compute h3, you have to have kernel of delta 3 and one more above, co-kernel of delta 4. But this is not giving us much information, so we have to look at how the filtration converges in the spectral sequence. So we had talked about how the filtration gives us the final page, and that is what is going to be helpful in determining the homology groups. So we have the delta maps which are come really easily, but now we have to have the long exact sequence. So as I said before, things have stabilized after page 2, and the anti-diagonal gives us the homology of the bigger space A. This is the bigger space A which contains B. So as I said before, HQ minus 1 of A, kernel of delta Q minus 1. So this Q minus 1 agrees with this, and this co-kernel is 1 higher. So for H3 you have kernel of delta 3 and this co-kernel of delta 4. So again this delta 3 comes from this position 1 2, and this co-kernel is lying at this position 0 3. There are other elements also which are lying on the diagonal, but they're all 0, so we ignore them. So now notice that this is our filtration to start with. So since this is our filtration right here, we can use our formula for the filtration for the infinity page. So what lies in column 0? So this is column 0, so this is column 0. So what lies here? So just by our formula from convergence of spectral sequence, you get image of HQX0 over image of HQX minus 1. This is just our formula, and this image of HQX0 is precisely, we talked about this before, how this HQX0 sits inside x1, and this is precisely how this HQX minus 1 sits inside x1 again. Now this x minus 1 is just a null set, so you don't have to worry about it. This is just a null set, and x0 you have set as b, so this is image of HQ of b. So we keep this in mind. What about column 1? So this is our column 1. So this column 1 is image of HQ plus 1 x1 over image of HQ plus 1 x0. So again this follows from our formula for infinity page. So see, this index q is q plus 0, this index q plus 1 is this q plus 1, and this is just our formula for formula arising from the filtration. So now, so for 0th you were considering this pair, now for 1 you are considering this pair, because you're going to talk about this higher pair x1. So column number is determining, so this number 1 here is determining this pair x1. So this is image of HQ plus 1 x1, but this is precisely how HQ plus 1 will sit in x1, but x1 is the biggest space, so it's just A, so it just sits inside by itself. So you have HQ plus 1 as A because x1 is A, and in the denominator you just put B. So again recall that so say we had some filtration, we had some space xn sitting inside this larger space x. So when we took the homology, we know this homology sits inside the homology of the larger space X, and we wanted to know how is the image of this sitting inside this. And the page infinity gives us the precise modular relations. So this is what is lying in the 0th column. So this is what consists of the co-kernel. So the co-kernel corresponds to this column here, the column 0. So the co-kernel is image of HQ minus 1b, we will write instead of HQB. That is precisely because this co-kernel has one index more. So this 2 is at position 0, 1. 0 plus 1 is 1, not 2. So this 3 corresponds to this position 0, 2. So 0 plus 2 is 2, not 3. Similarly, 0 plus 3 is 3. This 4 is 1 higher. So this co-kernel is sitting at a higher index, and that's why we write it like this. This corresponds to kernel here. So here we have seen it is shifted by 1, and this plus 1 shifting, you see this plus 1 shifting corresponds to this shifting C1, C2, C3, C4. So when you compute the homology here, it is shifted. So at position 1, 0, you get 1 here. Because this will give you H1 here. Here it will give you H2, H3, and so on. So notice that Q is the row number. So this is 0 here. So you get 1 here, and then 1, 1, you get 2 here, and 1, 2, you get 3 here. But notice that this index matches this index. This 1 plus 1 matches 2. 1 plus 0 matches 1. So we are not, but this is Q here. Q is right here. So we have to shift Q by 1 to get H1, because you have to add this first column to it. So here Q is 2, but your kernel is already at 1 above. So for kernel, we don't have to shift anything because it is already incorporating this 1. This 1 is the column number right here. So it is already incorporating it. So you write it as HQA over image of HQB. So basically copy this right here. Take into account that for the kernel you don't need this shifting. So now we want to construct the long exact sequence. So first we consider a general fact. So say we are given this exact sequence of modules like this, and we want to break it right here. So to break it right here, you break this module into two parts. You consider its image. So if this map coming in is phi, you consider the image of phi which sits inside it, and then you consider the co-kernel of phi. So this sequence you can split into these two exact sequences like this. So you can see this pictorially. So say that your module is given like this. So this is your mi minus 2. So you apply phi to it, and inside it sits mi minus 1. So this is precisely the image of mi minus 1. So this you can call as phi of mi minus 1, this green portion. And if you modulo this out, what you get is this portion. So that is the outside portion right here. And this is the coker of phi. And this was image of phi. And this coker of phi is precisely this. This is the definition of coker. So you combine this pink part with green part, this pink part with green part, you get mi minus 2. So these two sequences are equivalent to this sequence. If these sequences are exact, we need exactness because we don't want to miss any elements here or there. Now we are going to use this to construct the long exact sequence. So this is how our long exact sequence looks like. So this map phi I'm copying here, but this is just our delta q map. So you take this delta q map, you have to make the sequence exact. So only way to make this exact at this point is just put the image of phi here. So the sequence will become exact. We also have the sequence delta q minus 1. This we have, so this map here and this map here we have constructed on our page 2. So these maps we got from page 2. So now to make this sequence exact, we already have this map. You have to put kernel right here. So for any sequence going on like this, you have to make exactness here. You have to put kernel here. So this we are saying is kernel of delta q minus 1. And this you can see, this kernel, if you put q minus 1 here, so this is precisely, you see this kernel of delta q is given to us. Put q minus 1 here, and you will get this formula. Instead of q, you have q minus 1. And here you are just writing this. So now obviously you can glue these together. So notice that if you glue these together, you get mi minus 2. So you glue these together, you get this hq minus 1a. And that's how you get your long exact sequence.